Hello everyone, I'm Jian from Stony Brook University. Today I'm going to introduce the paper, Ultra Low Power Mode for Screenless Mobile Interaction. As we all know, power consumption is a major concern for mobile phone users and manufacturers. Some people might easily get in panic while their phone battery is low. For instance, while you're walking on the street and trying to reach your friend, however, your cell phone just had less than 5% battery. You might freak out and trying to reach your friend and then notify them, hey, I'm out of battery. I believe some of you guys might encounter such similar situations, right? So far, I had some sort of awful experience, which is really painful. I show you some example of the really panic case is that there's a very popular app called Die With Me. The whole purpose of this app is to allow panic users to text that their phone battery is gonna die. So you can see the message, the screenshot on the screen, so that they're really stressed and yeah. So we did a preliminary study, a survey of 35 participants by asking them what kind of task would you want to perform when the battery level is low. And you can see that 82% of the users, they would like to still perform text entry related apps, such as Gmail, WhatsApp, Messenger apps, stuff like that. However, for using phone camera or playing online video, few people do that, like 11% and 6%. Then we change the question by saying, if you are using Assistant X that drastically saves power when battery goes low, then what's your answer? So then we can see the result that almost all the users, they prefer using text entry related apps. And surprisingly, for using phone camera and playing online video, people, their desire of using those apps also increase. They both increase to 40% or 34%. So in this paper, we're gonna mainly focus on those three use cases so that to extend the hours, the time of playing this or running these three use cases. So therefore, our goal is the System X, which we call it Ultra Low Power Mode. It's short for ULPM. For it is designed for critically low battery status. As we know, the screen is always one of the most power-consuming components. So we did a preliminary study by changing the screen status, either by screen just totally turning it on, off, or by changing the brightness. And so the y-axis represents the hours of time playing the music. So the higher, the better. You can see that the first case, while we turn off the screen totally off, you can see that it almost lasts for 9 hours. That is because that the screen is turned off, so that the screen is not consuming power, and all the other apps is not running actively anymore. So the next two cases, by changing the brightness, either by 0% brightness or 100% brightness, it only lasts for like 3 to 4 hours. Why? The reason is that the screen is still turning on. So that is, the screen is still consuming significant power. Please notice here that the zero brightness is still have something display on the screen. It is the lowest brightness that user can reach by setting the Android or iOS phone. So another very interesting phenomenon is that by changing or by switching the screen, turning on and off for every 2 seconds frequently, actually it doesn't save power. It even drains power more quickly than the case of remaining 100% brightness. Well, the reason is that why you just keep changing turn the screen turning on and off, the UI, the app has to destroy this UI and reconstruct the UI back and forth, which induces more calculation and power consumption. So here's our goal. We're trying to minimize the power consumption by the screen. In order to minimize the power consumption by screen, ultra-low power mode supports screenless interaction. What does screenless mean is that you can still interact with your cell phone by turning off your screen. So, as we mentioned, we mainly focus on those three use cases, like using camera, or using the text entry cases, or playing online video. Why screenless? So that all the screen just being blank, just being turned off, but you're still able to interact with it. So here is the short demo video about how it is work. So the monitor and back just showing the real-time power consumption for each case. The left side is showing the screen on case. The right side showing the screenless case. You can see the big difference between those two in terms of power consumption. And the next is by taking video using camera. And this one is for listening online video. Okay, in order to achieve this goal, to do screenless interaction, we first need to solve the challenge. How to keep the phone interactive when the screen turned off. So I'll give you a concrete example. While you turn off the screen, so a user is editing a email on the Gmail app, while the user presses the power button on the cell phone. There are actually several procedures ongoing in the system. So first, this app UI gonna move to background of the UI stack, which is the module mainly maintain all the UI stack, open UIs. So at this point, UI gonna be moved to background, and then the operating system gonna destroy its UI, so that this app UI gonna be uninteractive and is not updating its UI anymore. So what do we do? In our case, we just by setting specific app as non-stop setters, for example, in this case, Gmail, so that this app still updating its UI, so that it is also remain interactive and keep refreshing its UI. And please notice here, this does not waste much power because you can see the remaining app still being destroyed. We're only setting specific app being active. However, after solving that, the typing event still failed to dispatch, like a user typing on the screen, it doesn't respond on that Gmail app. Why is it? Why the typing on that? The hardware composer gonna block out this typing event so that it won't be dispatched successfully on this Gmail. The hardware composer is a module for rendering the final image on the screen and maintain all the screen status. As long as it detects the screen being turned off, it's gonna block out so that nothing gonna happen on that. So what we do is by modifying the hardware composer to make it active to input events regardless of the screen status, whether either it is on or off. It's gonna let go and then typing the event gonna be dispatched successfully. So after solving the problem, there is another challenging, how to interact screenlessly. As we said, there are three main use cases that we are focusing on: text entry, using phone camera, and playing online video. As we can see that text entry is the most complicated case, which require very frequent visual feedback and interactions. So in this talk, I'm gonna mostly focus on this text entry case, screenlessly, how we do that. So the key idea of doing the text entry screenlessly is by leveraging the motor memory, as known as the muscle memory, and customizing the keyboard, and then enable the audio feedback. Before going through the solution, let's first look at what is the problem of typing screenlessly. Why in the screenless condition, they're more easy typing in the wrong place because there's no immediate visual feedback because everything is black. And user easily mistouching other UI parts, for example, like a delete button, which I don't want to. And it's also very hard to type the right word in the right way. And while you type the right word, it's also very hard to self-correct. So what we do, we design the ULPM keyboard to tailor the UI. You can see that we tailored the specific functionalities so that to avoid mistouching. And we place more blanks on the screen so that avoiding the mistouching on another part. So you can see here. And another point is that meanwhile, we use gestures to replace those functionality keys which had been removed. And another point that we leverage multiple memory. Please notice here that all the keys, all the alphabetical keys, they still remain in their original position. So that the user, because the user can memorize the keyboard position already. And we also tune the auto-correction model. Since white screen turned off in the screenless condition, users are more easily typing the wrong word. So we modify the keyboard decoder. And we also add audio feedback to read out what users have typed. And we did a study that this consumed negligible power. So we designed gestures for screenless typing for replacing those removed functionality keys. So like screen right, swipe right is committing word or just committing up space button. And swiping left is by deleting word by word, as the video is showing. So we implement the system by customizing Android 7 system to add ULPM feature. We implemented both on Nexus 5 and Nexus 6P for both user study and power evaluation. So here's a short video of showing how typing screenlessly.
The force is with you.
So the evaluation. We did power evaluation for text entry. You can see the y-axis represents the power consumption, so the lower the better. So we can see that instead of 100% brightness, even for 50% brightness and 0% brightness, screenless interaction on ULPM still outperform, saving drastically power up to 60%. And similarly, for the case of using camera or playing online video, ULPM in screenless condition also save power up to 40% of power. Then we go through user study. The first user study trying to answer the question, can users type when the screen is turned off? So we set up the user study by asking them to transcribe certain sentences. But why screenless condition, user couldn't know what they're gonna type, so we place a monitor to remind them. We're gonna just need to type, transcribe. So here's a result of the typing speed. You can see that ULPM in screenless condition, user in average, they can achieve over 30 words per minute, which is a surprising speed regarding of the screenless condition. And the error rate is below 10%. So we conduct the second user study to answer the question, can users center an object in the video capture when the screen is turned off? We set up the user study by asking them to capture a 20-second of video by holding the smartphone to target at this QR code to make it as center as possible in that video. And then we analyze those 20-second video to show their pixel deviation from the center, from the object that you captured and to the center of your screen. And so here's the result of showing the pixel from the center. So the lower is the better. So we analyze showing that the average difference in offset is approximately 0.9% of the image size, which means that ULPM screenless mode has minor effect on capturing video. So the conclusion, we designed an ultra-low power mode system for screenless interaction, and we make app interactive when the phone is screen turned off. And we're leveraging multiple memory to support screenless text entry, and the results show ULPM drastically save power consumption. Thank you for your attention.
So there are two microphones in the room. There's one over on this side and one in the middle. If you have a question, please step up to the mic. Go ahead.
Hi,
please.
Gregory About. Good motivation for your work. And looking at what you did with the screenless text entry, I wondered if you considered two options that kind of immediately suggest themselves using audio, so using the microphone instead of typing? And what about just putting a physical overlay on the phone of the keyboard? Did you look at those options?
Yeah, so that's very good point. Like just put some like 3D printing with some very transparent, some assistive technology to remind users. That could be a very good inspiration. So we considered that before, but I think in order to make it more, apply to more cases that users don't need to bring something like to assist them, we first didn't consider that much. But I think that can be regarded as a future work of that. Yes, that's a good point.
Great. So maybe there's a question over here.
Hi, Ulrich Zado from Code University Berlin. I wonder, so some of the things you're doing are probably similar to user interfaces for the blind. Have you considered those as well?
Exactly. We had a continuous work by applying this to the blind user or visually impaired users because they're really cautious about their power consumption because they're always carrying power bank. The second is that they're really cautious about they might be shoulder surfing because while they're typing, they're afraid that some other guy, they might pass by and see what they've typed. So they really want that system actually. So we are doing that. Yeah.
Okay, but if you turn it around and sort of say, what of the current user interfaces for the blind could you maybe reappropriate for what you're doing? Have you thought about that?
You mean how to redesign that to make it appropriate for disabilities?
How to redesign systems meant for the blind to be power saving. So to use them in the context of you don't have a screen, which is basically what blind people have, right?
Yeah. Yeah, so how to coach them to better utilizing the phone to saving power, that's a very a good direction. So far, we didn't consider that specifically because first, they have a lot of misunderstanding because they feel like while you're turning off the screen or just making most of the time, they even just randomly slide the brightness so that which doesn't save power, or even full brightness, 100% brightness, which is really drastically disaster. So, yes, I think that's a good point that we should come up with a mechanism to coach them to better utilizing that.
Okay, thanks.
Thanks.
Yeah, we have time for one more question. Andy? Unless it's a really quick question.
Really quick one.
Okay.
Have you considered OLED displays? Like they have an interesting property?
Yeah, that's a good point. So actually, AMOLED is totally different technology, which is our next project trying to partially display that keyboard because partial display gonna save power as well. But for LCD, it doesn't work. It doesn't save power at all. That's a good point. Thanks, Andy. Okay.
I think, is it a short question? We have a...
Yeah, so some of the techniques you use to turn the screen down, have you thought about making them available as an API so other developers could add those capabilities?
Yeah, I think it's possible. Since it is more low-level hacking, so that we think it is better like to collaborate with some manufacturers to let them to apply this technology to make it more available to others. Yes. Thanks.
Great. Let's thank our speaker once more.